I want to talk about some concentration definitions. So the most important one is definitely molarity. So molarity is represented by a capital M. So molarity is defined as the moles of solute per liter of solution. So for example, if I had a 5-liter bottle of solution and I had 5 moles of sodium chloride in it, the concentration of sodium chloride would be 1 molar, so 1 with a capital M next to it. So 5 moles divided by 5 liters equals 1 molar. 1 molar. Okay? One big M. So there's another one that's a little less common. So molality. So molarity, molality. So molality is a lowercase m, and it's given by moles of solute divided by kilograms of solvent. So if I took 5 moles of sodium chloride and I dissolved it in 5 kilograms of water, I would have a 1 molal solution. Okay? And so I want you to notice this. This is very important. So molality is based on kilograms of solvent, and molarity is based on liters of solution. So the solution and solvent are not necessarily the same thing. Okay? And it turns out that molarity and molality will actually differ quite significantly at very, very high concentrations. At low concentrations, we can assume that the volume does not change when we add solute. So when we add a solute to water, we assume that the volume does not change. So this means that 1 liter of solution will be about the same as 1 kilogram of solvent. So molarity and molality should be the same at low concentrations. Okay? So the reason why we do this is because molality is used in calculations that depend on temperature. Okay? Because as the temperature changes, the volume of the solution will actually change. You know, water will expand when it heats up, and it will contract when it cools down. So this is why we need to use molality, which uses weight, which mass, which will not change on temperature. So this is why we use molality sometimes. Another important one is ppm or ppb, so parts per million or parts per billion. So often if you look at like drinking water regulations, you'll see like they say, oh, we can have this much lead in parts per million, or like this much mercury in parts per billion. So, and typically this is by weight. With gases, it might be by volume. So this means by weight, I mean mass. So 1 part per billion would mean 1 nanogram of solute per gram of solvent, okay? Or parts per million, so that's like 1 microgram per gram of solvent. So it just means like 1 millionth of a part of solute per part of solvent, right? Okay, with these definitions in mind, let's do some problems. So I have 4 problems here, and the first one's actually a little tough, so I'll just do it out for you. So a concentrated solution of CaCl2 has density equals 1.234 grams per milliliter and a molarity of 2.719 molar. So these are completely made up numbers, so don't try this yourself. So we want to calculate the molality. Great. So this is the data we're given. So we have the density. So density is usually given by the Greek letter rho. So rho equals 1.234 grams per milliliter. And we're given that we have 2.719 moles per liter of CaCl2. Okay? So what can we do with this data? So we have 2.719. Okay, so we have this. This doesn't look very useful, but what we can do is we can convert this to grams. So can someone tell me the molar mass of calcium chloride? So look at your periodic table and tell me the molar mass of calcium chloride. I will put one here. So remember there are two chlorines. There's two chlorines, not one, right? It's CaCl2. So. 110.9, I think that's right. Yep, that should be right. Okay, so we have that the molecular weight of equals, okay, so we multiply this by our conversion ratio. This cancels out. Equals, let's see what it is. Okay, great. So now we know that the mass of calcium chloride is going to be 301 grams per liter. Now, how much does 1 liter of solution weigh? I mean, how much does it mass? Technically, grams are a unit of mass, not weight, but whatever, it doesn't matter. So what's the mass of 1 liter of solution? So remember our density here. So what's the mass of 1 liter? So we know the density and we know the volume. So rho times, so how many liters are in a milliliter? How many liters are in a milliliter? It's, wait, so there are 1,000 milliliters in a liter, right? So, right? So we need to multiply rho by 1,000, I'm sorry, by 1 liter per, what? Yeah, sorry. So rho multiplied by 1,000 milliliters per liter gives us this, okay? So now we have two weights. The total mass of the solution is 1,234 grams per liter, and the mass of the calcium chloride is 301.5 grams per liter. There are only two things in our solution. There's water and there's calcium chloride. So can someone tell me the weight of the water? How much does the water in our solution weigh? So how much does the water in the solution weigh? So the total mass is 1,234. And the mass of the calcium chloride is 301. So therefore, the mass of the water should be the difference, right? So 932.5. Okay, so we have that. So great. And now we want to calculate molality, which is based on kilograms. So can someone convert this to kilograms? So can you convert this into kilograms? Great. So 0.9325 kilograms of solvent. Now we need the number of moles, and it turns out that we already have that number. The number is given to us. So we already know we have 2.719 moles. So therefore, the molality is 2.719 divided by 0.9375 equals so 2. Okay, so we have a molality of 2.9. So you can see we have a very concentrated solution of calcium chloride. We have 300 grams per liter. That's a lot, right? So you can see with these very concentrated solutions, we can often get significant deviations between the two, our two numbers, 2.9 versus 2.7. So let's move on to so we have 3 other problems. So how much time do you think how much time do you want to do these problems? 3 problems. Wait. What? Wait. Hold on a second. Yep, so we have these 3 problems. So how much time do you want for those? 15 minutes? Or what do you think? Do you think 15 minutes are good? Okay. So we can do these 3 problems, and I'll give you 15 minutes to do them, okay? So this one, and this one. First, can someone tell me the molar mass of NaCl, so sodium chloride? The molar mass. What's the molar mass? Let me make sure that's right. I don't think that's right. You're off by a little bit. You check. Yeah, 58.45. So Angela, can you check your numbers there? I think you might have just typed something wrong in the calculator. Okay, so we know the molar mass of sodium chloride. Now, we also know the weight of sodium chloride. We have 40 grams. Now, can someone tell me how many moles of sodium chloride we have? How many moles do we have? Uh, 0.684. Let me make sure that's right. Yep, great. 0.684 moles. Fantastic. Now, molarity is defined as moles per liters of solution, and we are not given the volume of the solution. However, I did say that we assume that the volume does not change. So, and for most cases, you can do this actually. So, can someone tell me what the volume is in liters? In liters? What's the volume in liters? What will be the volume in liters? Because right now the volume is given in milliliters, so we need to find it in liters. Great, 0.765 liters. Good. Okay, so 0.765 liters. So what's the molarity? What's the molarity? So moles per liter. So what's the molarity? What is the molarity? 0.9. Yeah. So remember your sig figs. So it should be 0.89, but yeah, 0.9. It's fine. Great. Okay. So that's the first one. So all we do is we divide the number of moles by the number of liters, moles per liter, right? Great. So how many mils of water do we need to dilute a 1,337 milliliter sample of 3.45 molar sulfuric acid to 0.234 molar? Okay. Well, okay. So the first step is we need to find some kind of constant. So remember that the number of moles will always be a constant in this dilution since we're not adding anything, right? We're not adding anything, so thus the number of moles is a constant. Now, how do we find the number of moles? Well, can someone tell me how to find the number of moles in this situation? What should we do with the numbers we're given? Number of moles. Well, I can give you a hint. So the concentration C equals the number of moles N divided by V, right? Per our definition of molarity. So how do we find a number of moles if we're given the volume and the molarity? Well, the number of moles is just the volume multiplied by the concentration. Of course, this has to be in liters, so the concentration in liters. So what's the conclusion from this? So what's the conclusion? Okay, so concentration equals okay, so then therefore C1 V1 equals E2 V2, and we need to find the new volume. So we know the initial state and we know the new concentration. So we need to find this. So V2 equals C1 V1 over C2. And then what does this equal? So can someone tell me what that equals? So what does V2 equal? So you already know what C1, V1, and C2 are. So I said that C1 and V1 are the initial concentration and the initial volume. And we know the final concentration, C2, so 1,337 times 3.45 divided by 0.234 equals 1.97 times 10 to the fourth milliliters. Okay? So we have the final volume. This is the final volume. And we make the assumption that volumes are additive. We make strictly speaking, you cannot add volumes, but we can make the assumption here. Okay, so we started off with 1337 milliliters, and we need to get 19700 milliliters. So therefore, how much water should we add? So 19700 minus 1337 equals 18360. Okay? So this is how much water we need to add. Okay? Look at the final question. Okay. So as the first step, can someone tell me what are the molar masses of these compounds? Oh, I made another typo. I made a typo. Let me fix that. That should be a 3, okay? Can someone tell me the molar masses? What are the molar masses of all of these compounds? So what's the molar mass of sodium chloride? Okay, 58.45, great. What about sodium sulfate? Can you check that again? Great, yeah, 141.8. So remember that there are 2 sodiums and 4 oxygens, which I think might be where the mistake is coming from. I'm not sure. Oh, wait, let me check something. Times 2. I think I know what your mistake is. Let me just check it. Okay. Yeah, I don't know. Okay. Okay, yeah, 141.8 is correct. And what about sodium phosphate? Can we do sodium phosphate? Yep, 163.6. Perfect. Okay. Now, we need to, molarity is not defined using grams. Molarity is defined with moles. So we need to convert these grams to moles. So can someone tell me how many moles of stuff we have? So how many moles of sodium chloride do we have? All we need to do is take, okay. So I put all the data we have here. Okay. So we have 10 grams of NaCl times 1 mole per 58.45 grams, right? And then this equals 10 divided by 50 times 10 to the minus 1 moles. Okay, now can someone do the same thing for the other two? So do these two. Someone tell me how many moles of sodium phosphate and sodium sulfate do we have? "20 grams of sodium sulfate so 20 grams of sodium sulfate times 1 mole divided by 141.8 grams equals 0.141. And we just do the same thing. So 30 divided by 163.6 equals okay, so we have our three numbers. Great. So how many moles of sodium do we have per mole of sodium chloride? So if I have 1 mole of sodium chloride, how many moles of sodium do I have? Look at the chemical formula. Okay. So how did you get 0.5? Right. So when I say I have 1 mole of sodium chloride, that means I have 1 mole of formula units. Okay? So 1 mole of formula units. So 1 mole of these formulas things. So each formula unit contains 1 mole of sodium, right? Sodium. Because there's no coefficient on the sodium, which means that there's an implied 1. Therefore, I have 1 mole of sodium per mole of sodium chloride. What about sodium phosphate, sodium sulfate? How many moles of sodium do we have per mole of sodium sulfate? Oh, wait, can you, that's a 2, not a 3, right? I didn't write that clear. Yeah, that's, so does everyone see why this, we have 2 moles of sodium per mole of sodium sulfate? What about sodium phosphate? How many moles of sodium do we have per mole of sodium phosphate? Three, exactly, great. So therefore, you agree that the total number of sodium ions is the sum of all of the parts, right? So therefore, N plus equals 1 times N plus 2 times N of sodium sulfate okay, and then this equals 0.171 plus 2 times 1.1 plus 3 times 0.183, and then this equals some number. So and this equals 1.002. Okay, so this is the total concentrate. So we have 1.002 moles of sodium. However, the question did not ask for moles of sodium. it asks for moles, it asks for the concentration. So we're given the volume. We're given the volume. So can someone tell me the concentration? So we know the number of moles. We have 1 mole, and we have the volume. So what's the molarity? By 3.14 is 0.318. Perfect. Okay, so yeah, so that's how we do that. Okay, so I will definitely post more of these practice problems online later. Okay, and now I just want to briefly talk about a little bit of non-aqueous solutions. So far we've only been talking about stuff dissolved in water because most of the things you'll encounter will be dissolved in water. Water is what's called the universal solvent for some strange reason, because it dissolves a lot of stuff. But in my opinion, I think that non-aqueous solvents are more important because these appear in organic chemistry. And so they have a much more, and even in organic chemistry, we see like very strange solvents like liquid HF, liquid SO2, or like glacial acetic acid, so very strange solvents. So these non-aqueous solutions appear all the time in all different fields of chemistry. So, because not everything dissolves in water. If you've ever tried to make a vinaigrette, which is made by mixing oil and water, you know that they don't mix. You have to shake it quite a lot to get it to kind of mix. So, so for nonpolar compounds, we want to use nonpolar solvents. For polar compounds, we want to use polar solvents. And this is the idea of like dissolves like. So remember in the last lecture, we talked a little bit about polarity. So electronegativity differences that cause partial charges. So water tends to dissolve polar substances. So for example, ethanol, methanol, or glucose. So those have the oxygen bonded to H. So very polar bond, and the oxygen has a very good partial negative charge. And we have some hydrogen bonding. So water loves to hydrogen bond with compounds. So that's why water can dissolve that stuff. And water also is good at dissolving charged compounds. So your ionic compounds made from ions, so sodium chloride and etc. But what about compounds that are nonpolar, that don't have polar bonds and are not made of ions? For example, benzene. So benzene is completely made of carbon and hydrogen, so it's a pure hydrocarbon. Hydrogen and carbon have very, very similar electronegativities. So there's no bond polarity at all. There's no partial negative charges and no partial positive charges. Benzene will not dissolve in water. So we need nonpolar solvents. So so I have a picture of like an organic setup. So we have a bottle of butyl lithium. So butyl lithium is very, very, very flammable. So you have to use this very fancy airtight apparatus. So butyl lithium is often sold in solutions of hexane. So hexane is another compound made entirely of carbon and hydrogen, so very nonpolar. So this is a solution of butyl lithium and hexane. I wanted to demonstrate this polarity. I found this nice picture. So we have a compound here called Bruker's merocyanine. And Bruker's merocyanine exists in this resonance between two different structures, okay? And as you can see, one of the structures exhibits these charges, right? And then the other structure does not have those charges. Therefore, this form will be more prevalent in polar solvents, right? Because the charges are stabilized by the by the solvent. But in here, this is nonpolar, relatively nonpolar, so it prefers to be in more nonpolar solvents. So as you can see, we have this transition from blue to yellow. So on this side, we have our very polar solvents, water, acetic acid, and methanol. And here we have somewhat more nonpolar solvents. So DCM, so dichloromethane, acetone, dimethyl sulfoxide, and in between we have the intermediate solvents. So isopropanol, rubbing alcohol, and ethanol, drinking alcohol. So looking at this picture and this picture, which one of these structures do you think is yellow and which one is blue? So is the structure on the left yellow or the structure on the right? Great. So the one on the left should be yellow because it likes to be in polar solvents, and in polar solvents it's yellow. What? Finally, we have colligative properties. We don't have much time left, so I'll just breeze through these. So basically, colligative properties are properties of a solution that depend on the concentration. So the two most important ones you need to know are boiling point and freezing point depression. So this means that a solution, we have the boiling point of a pure solution, of a pure solvent, and when we add a solute to that solvent, the boiling point will increase. Additionally, the freezing point will decrease. And this increase or decrease is directly proportional to the concentration of the solute. So it's equal, so the depression or elevation, so it's boiling point elevation and freezing point depression. So the boiling point will go up and the freezing point will go down. So write that down. So the elevation or depression is equal to some constant. So the freezing point constant or the boiling point elevation constant multiplied by the concentration of solute. And these constants are unique to each solvent. Furthermore, we have osmotic pressure. So this works on the idea of osmosis. So the solvent will want to pass through a semi-permeable membrane, and the solute cannot pass through that membrane. So the solvent will move to try to equalize concentrations. So it will exert a pressure, which is equal to the osmotic pressure. And the osmotic pressure is very sensitive to low concentrations. So when they were studying proteins back in the 1900s, early 1900s, this is how they found the molar masses of proteins, because proteins have very, very high molar masses in the tens of thousand range. So maybe like 50,000 grams per mole. So naturally, the concentrations are going to be very, very low. So we cannot use boiling point elevation or freezing point depression since we won't be able to measure the change. But we can use osmotic pressure because it's very sensitive. And finally, the vapor pressure will change. But when we add a solute to a solvent, you can think of it as diluting the solvent in a sense. So we're almost diluting the solvent. And this lowers what's called, remember, the mole fraction of the solvent. So the number of moles of solvent divided by the total number of moles. Hence, the vapor pressure will actually decrease when we add a solute. But for now, don't worry about these too much. I just wanted to introduce them. So finally, we can do these AP review problems. So these are AP-based problems. And we really don't have much time left. So how about I just go over all of them, and then you can do more practice problems by yourselves. So let me get some clean paper since I don't have any. Cadmium chloride is 140 grams per 100 milliliters. So calculate the molar solubility. So cadmium chloride equals, so we have 112 plus 35.45 times 2 equals equals 181. Okay, so 140 grams times equals 0.773 equals 7.73 molar. Okay, so that's how you do that calculation. So which of the following is most soluble in hexane? So do you think hexane is polar or non-polar based on the formula here? Is it polar or non-polar? Hexane. So hexane only contains carbon and hydrogen, which have very similar electronegativities. So it's nonpolar, right? Now, NaCl is an ionic compound. It has charges, so it will not dissolve in a nonpolar solvent. This one is also polar. We have this oxygen and this hydrogen. But this one, benzene, will dissolve in hexane because it's very nonpolar. You can see only carbon and hydrogen. Like dissolves like. So pure hydrocarbon. They're like dissolves like. Great. And water is, of course, very polar. Okay. Now, 3.45 moles and 1.25 moles of hexane are mixed. What information do we need to determine the molar concentration? Okay. 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 So we need to know the moles divided by the liters. So we need to know the volume. So the volume is equal to the mass times the density, right? Do you see? So density is mass divided by volume. So volume equals mass times density, right? I think that's right. Wait, let me check that. So volume is mass divided by density. That's my bad. So volume is mass divided by density. So that's my bad. So we need to know the mass and the density. So since we already know how many moles there are, to find the mass, all we need to know is the molar mass, right? So we need to know the molar mass and the density. Now, the density of hexane is not good enough since we have this phenyl chloride here, and the density of hexane tells us nothing about the phenyl chloride. So we can rule that out. And temperature has no effect since the temperature will not be able to tell us what the density is, okay? And I think the last one is pretty, it's the same, it's basically the same thing as this one. So do we have any questions about anything?